Right now, more than 15 billion miles from where you are sitting, a spacecraft the size of a small car is drifting through interstellar darkness at 38,000 miles per hour. Voyager 1 has been flying away from Earth since 1977. It has never stopped, never slowed down in any meaningful way, and never turned around. By November of 2026, a radio signal from Earth will take a full 24 hours just to reach it. Here is the question almost nobody thinks to ask. Could we catch it? Not match its distance, not pass the line it crossed decades ago, actually chase it down, intercept it, and touch it again? The answer is far stranger than you expect. If you enjoy journeys that change how you see the cosmos, hit that like button and subscribe. It means more than you know, and it helps these stories reach more curious minds like yours. Now, settle in, get yourself comfortable, let's begin. Picture something the size of a compact car. Not a truck, not a bus, not the towering multi-stage rocket that carried it off the planet. Just a small aluminum frame with a big white dish antenna bolted to the front, a trio of slender booms extending outward like insect legs, and a body crammed with instruments built from technology older than most of the people listening to this right now. That object weighs about 722 kilograms. It has no wings, no aerodynamic shape, no windows. If you placed it in a parking lot next to an actual car, you would not look twice. And yet right now, at this moment, that unremarkable machine is farther from Earth than anything human beings have ever built, ever launched, or ever touched. Its name is Voyager 1, and it is not coming back. As of mid-2026, Voyager 1 is approximately 163 astronomical units from the Sun. 1 astronomical unit is the distance between the Earth and the Sun, roughly 93 million miles. Multiply that by 163, and you begin to grasp the problem. Voyager 1 is more than 15 billion miles from home. If you could somehow stretch a highway from Earth to the spacecraft, you would need to drive at 60 miles per hour without stopping for more than 28,000 years to reach it. That number is not a metaphor. It is arithmetic, and the distance is growing every single second of every single day, because Voyager 1 has not stopped moving since the moment it left Cape Canaveral on September 5th, 1977. Its speed is approximately 17 kilometers per second relative to the Sun. That translates to roughly 38,000 miles per hour, or about 61,000 kilometers per hour. In the context of everyday life, that is staggeringly fast. A bullet fired from a high-powered rifle travels at roughly 2,600 miles per hour. Voyager 1 moves more than 14 times faster than that bullet. But in the context of space, 17 kilometers per second is modest. It is fast enough to escape the Sun's gravity, which is the entire point. It is not fast enough to reach any nearby star in fewer than tens of thousands of years. And it is a speed that Voyager 1 did not earn through any engine it carries on board. That detail matters enormously to the story of catching it. Voyager 1 was never designed to be the fastest outbound spacecraft in history. It was designed to visit Jupiter and Saturn. The original mission plan grew out of a rare alignment of the outer planets that occurs roughly once every 176 years. In the late 1960s, aerospace engineers at the Jet Propulsion Laboratory realized that a spacecraft launched in the late 1970s could use the gravity of one planet to sling itself toward the next, hopscotching across the outer solar system without needing enormous amounts of fuel. The concept was called the Grand Tour, and it relied on a trick of orbital mechanics known as the gravity assist. When a spacecraft flies past a planet on the correct trajectory, it can steal a tiny amount of that planet's orbital momentum. The planet, being trillions of times more massive, loses an imperceptible fraction of its speed. The spacecraft, being tiny, gains a tremendous boost. It is the same principle that makes a tennis ball bounce faster off a moving car than off a stationary wall, scaled up to planetary dimensions. The Grand Tour window was a gift from celestial mechanics, and it was not going to wait. If NASA missed the launch window in the late 1970s, the next opportunity would not arrive until the 22nd century. But the agency was in a difficult position. The early 1970s were not kind to NASA's budget. The Apollo program had ended. Public enthusiasm for spaceflight was fading. Congress was cutting funding, and the ambitious Grand Tour proposal, which originally called for 4 spacecraft visiting all 5 outer planets, was slashed to a more modest mission called Mariner Jupiter-Saturn. 2 spacecraft would be built. They would visit Jupiter and Saturn only. The grander ambitions of reaching Uranus and Neptune were officially set aside, though the engineers who designed the trajectories quietly preserved the option in case the spacecraft survived long enough to use it. Those 2 spacecraft were eventually renamed Voyager 1 and Voyager 2. They launched within weeks of each other in the summer of 1977, not as the grand flagship mission that engineers had dreamed of, but as a scaled-down compromise that Congress was willing to fund. Nobody at NASA expected either spacecraft to last more than 5 years. The primary mission was designed to end after the Saturn encounters. Everything that followed, every discovery, every record, every milestone, was a bonus that no one planned for, and no budget anticipated. Voyager 1 used the gravity assist trick twice. It flew past Jupiter in March of 1979 and received a massive velocity kick that reshaped its trajectory and flung it towards Saturn. The Jupiter encounter alone transformed the mission. Voyager 1 photographed the Great Red Spot in detail never seen before. It discovered active volcanoes on the moon Io, the first time volcanic activity had been confirmed on any world other than Earth. It revealed that Jupiter's faint ring system existed. Every image it returned rewrote some piece of planetary science, and the gravity of Jupiter, indifferent to the beauty of its own moons, flung the spacecraft onward at a speed no chemical engine aboard could have provided. It arrived at Saturn in November of 1980, and what it found there was so astonishing that it reshaped not only planetary science but also Voyager 1's entire future. Before Voyager, Saturn's rings were understood as a handful of broad bands separated by a few gaps. Telescopes from Earth could resolve perhaps half a dozen distinct features. Voyager 1's cameras revealed something entirely different. The rings were not a few broad sheets. They were thousands upon thousands of individual ringlets, nested inside each other like the grooves on a vinyl record, extending outward in a complexity that no model had predicted. What had looked like smooth bands from Earth turned out to be a vast, intricate structure with gaps, density waves, and braided features that seemed to defy simple orbital mechanics. Some ringlets were eccentric, slightly elliptical rather than perfectly circular. Others showed kinks and clumps that moved around the ring like traffic jams on a circular highway. The narrow F-ring just outside the main ring system turned out to be shepherded by 2 tiny moons orbiting on either side of it, their gravity confining the ring particles into a narrow band. Scientists had never seen anything like this. The moons were later named Prometheus and Pandora, and their gravitational interaction with the ring created braided, kinked structures that looked almost alive. The rings were not static structures, they were dynamic, evolving, shaped by gravitational interactions so subtle that understanding them would take decades of additional study. And then there were the spokes. As Voyager 1's cameras watched the rings rotate, dark radial features appeared, stretching across the bright B-ring like the spokes of a wheel. They should not have existed. Orbital mechanics dictates that material closer to Saturn orbits faster than material farther out. Any radial structure should shear apart within minutes as the inner material races ahead of the outer material. Yet the spokes persisted, rotating with the ring as if painted on a solid disc. They appeared, lasted for hours, and then faded. Scientists eventually attributed them to tiny charged particles levitated above the ring plane by Saturn's magnetic field. But at the time of the encounter, they were simply impossible. They violated intuition, violated models, and demanded new physics to explain. The spokes alone justified the entire mission. Beyond the rings, Voyager 1 turned its attention to Titan. This was the moon that would determine the spacecraft's fate. Titan was the largest moon of Saturn and the second largest moon in the entire solar system. It was the only moon known to possess a substantial atmosphere, a thick shell of nitrogen and methane that ground-based telescopes had detected but could not penetrate. What lay beneath that orange haze was entirely unknown. Some scientists speculated that Titan might have oceans of liquid methane on its surface. Others proposed a landscape of hydrocarbon ice. The uncertainty was maddening. Titan was a world wrapped in mystery, and the only way to begin unwrapping it was to fly close enough to study its atmosphere directly. Mission planners faced a choice. They could aim Voyager 1 for a close flyby of Titan, passing within 4,000 kilometers of the Moon's surface to study its atmospheric composition, temperature, and pressure. Or they could skip Titan and redirect the spacecraft toward Uranus and Neptune, continuing the grand tour of the outer planets. The two options were mutually exclusive. The flyby geometry required to pass close to Titan would bend Voyager 1's trajectory so sharply that no further planetary encounters would be possible. If they chose Titan, they would gain one of the most scientifically valuable encounters in the mission. If they skipped it, they would preserve the option to visit 2 additional planets that no spacecraft had ever seen. They could not do both. They chose Titan. The scientific case was overwhelming. An atmosphere like Titan's, rich in organic chemistry and exposed to solar ultraviolet radiation, was thought to resemble the conditions on early Earth before life began. Studying it could offer clues about the chemical processes that preceded biology. No other target in the solar system offered this specific opportunity. Uranus and Neptune were important, but they could wait. Voyager 2 was still behind Voyager 1, on a slower trajectory that could be adjusted to visit the ice giants if Voyager 1 took the Titan assignment. The decision was made. Voyager 1 would sacrifice the grand tour to study one extraordinary moon. The flyby delivered. Voyager 1's instruments measured Titan's atmospheric pressure at roughly 1.5 times Earth's sea level pressure, far higher than expected. The atmosphere turned out to be almost entirely nitrogen, with a few % methane and traces of complex organic molecules. The temperature at the surface was roughly minus 179 degrees Celsius. The orange haze that obscured the surface was composed of tholins, complex organic particles formed by ultraviolet radiation breaking apart methane, and nitrogen molecules in the upper atmosphere. Voyager 1's cameras could not see through this haze. The surface remained hidden, but the atmospheric measurements alone confirmed that Titan was one of the most chemically complex worlds in the solar system, a natural laboratory for prebiotic chemistry operating on a planetary scale. Those measurements would drive decades of follow-up research and eventually lead to the Cassini mission's deployment of the Huygens probe, which landed on Titan's surface in 2005 and found a world shaped by flowing liquid methane. But the choice that made all of this science possible also sealed Voyager 1's trajectory. The flyby geometry required to pass close to Titan bent the spacecraft's path sharply upward, 35 degrees above the flat plane of the solar system, called the ecliptic. After the Saturn encounter, there were no more planets ahead. No Uranus, no Neptune, no Pluto, just open space, a rising trajectory aimed in the general direction of the constellation Ophiuchus, and a velocity of 17 kilometers per second that the Sun's gravity would never fully claw back. The same encounter that gave humanity its first close look at Titan's atmosphere also created the intercept problem that makes catching Voyager 1 so punishing. The 35-degree inclination, the 17 km per second escape speed, the heading toward Ophiuchus, all of it traces back to a single decision made in 1980 about a moon shrouded in orange haze. The science and the trajectory are inseparable. You cannot have one without the other. Every extraordinary measurement Voyager 1 returned from the Saturn system is also a line on the trajectory plot that carries it farther from Earth every second, at a speed no other outbound spacecraft has matched, along a path no other mission has followed. That is the speed it carries today. Not because of a powerful engine, not because of fuel it burns, because of 2 planetary encounters that happened decades ago. Voyager 1 has been coasting on borrowed momentum for more than 46 years. Its thrusters, tiny hydrazine attitude control jets designed only to keep the antenna pointed at Earth, have no ability to accelerate it further. They have no ability to slow it down. The spacecraft is, in every practical sense, a thrown stone. It was hurled by Jupiter and Saturn, and it has been sailing ever since, and nothing in the universe is acting to stop it. This is the first thing you must understand about the problem of catching Voyager 1. Its speed is not a product of its technology. It is a product of its history. The same trajectory that gave it that speed also sent it on a path that no future spacecraft would naturally follow unless a mission was specifically designed to chase it. Voyager 1 is not heading toward any star in particular. It is not following any useful route through interstellar space. It is simply flying in the direction that the Saturn flyby pointed it, drifting northward out of the plane where all the planets orbit, moving farther from any gravitational body that could serve as a stepping stone for a pursuer. And here is the detail that makes the problem quietly terrifying. Voyager 1 covers roughly 3.5 astronomical units every year. That is 3.5 times the distance from the Earth to the Sun, added to its lead every single year. Think about that number for a moment. In the time it takes Earth to complete one orbit, Voyager 1 moves 325 million miles farther away. Each year that humanity waits to launch an intercept mission, the spacecraft gains another 325 million miles of distance that a future pursuer must erase. This is not a target sitting still and waiting to be reached. It is a target that has been sprinting away for nearly half a century, and the sprint never ends. By November 18th of 2026, Voyager 1 will cross a milestone that puts this distance into visceral focus. On that date, the spacecraft will be exactly 1 light day from Earth. That means a radio signal traveling at the speed of light, 186,000 miles per second, the fastest anything can move in this universe, will take 24 full hours to travel from a transmitter on Earth to the spacecraft's antenna. If mission controllers at the Jet Propulsion Laboratory send a command to Voyager 1 on a Monday morning, the spacecraft will not receive it until Tuesday morning. If it responds immediately, Earth will not hear the response until Wednesday morning. A simple back-and-forth exchange now takes 2 entire days. This is not a communication inconvenience. It is a direct physical measurement of how far away the spacecraft already is. And while those 2 days pass, Voyager 1 moves another roughly 1.8 million miles deeper into interstellar space. The signal itself is astonishing in its fragility. Voyager 1's radio transmitter operates at roughly 22 watts of power. That is comparable to a refrigerator light bulb. This faint whisper crosses 15 billion miles of vacuum and arrives at Earth's deep space network antennas with a power level measured in fractions of a billionth of a watt. The only reason we can still hear it at all is that NASA operates some of the most sensitive radio receivers ever built, massive dishes 70 meters across in California, Spain, and Australia, constantly listening for the faintest trace of that signal. Even with those instruments, the data trickles in at roughly 160 bits per second. For comparison, a modern internet connection delivers data millions of times faster. Voyager 1's link to Earth is a thread, not a cable, and that thread is stretching thinner every year. The heliopause crossing is another critical landmark in understanding Voyager 1's position. In August of 2012, Voyager 1 became the first human-made object to leave the heliosphere, the enormous bubble of charged particles and magnetic field that the Sun blows outward into space. Inside the heliosphere, the solar wind dominates. Outside it, interstellar space begins, a region filled not with the Sun's particles but with the thin plasma and cosmic rays that drift between the stars. Voyager 1 did not blast through this boundary. It drifted across it at the same steady 17 kilometers per second it has maintained for decades. Scientists confirmed the crossing by measuring changes in the plasma density around the spacecraft. The interstellar medium turned out to be denser and more complex than many models predicted, and Voyager 1's instruments recorded details that no telescope on Earth could observe. What Voyager found at the boundary contradicted expectations in several important ways. Scientists had predicted that the magnetic field direction would rotate sharply at the heliopause, shifting from the Sun's magnetic orientation to the orientation of the local interstellar field. It did not. The field direction changed far less than models required, creating a puzzle that remains partially unresolved. The plasma density did increase dramatically, confirming the crossing, but it fluctuated in ways that suggested the boundary was not a clean line but a ragged, dynamic frontier where solar and interstellar material jostle against each other over distances of hundreds of millions of miles. Voyager 1 also detected what scientists described as plasma waves, oscillations in the electron density of the interstellar medium that could be converted into audible sound. When those signals were processed and played through speakers on Earth, they produced an eerie rising tone, the actual sound of interstellar space vibrating around the spacecraft. No other instrument has ever recorded anything like it. No Earth-based telescope can detect these oscillations. They are only measurable from inside the medium itself, which is exactly where Voyager 1 is, and exactly where no other spacecraft can reach. This is why catching Voyager 1 is not merely a question of engineering pride. The data it returns from interstellar space is scientifically irreplaceable. The instruments aboard Voyager were designed for planetary encounters in the 1970s, not for interstellar research, and yet they have revealed phenomena that dedicated interstellar instruments have never observed because no dedicated interstellar instruments have ever existed at that distance. Every measurement Voyager 1 sends home is a first. Every reading is taken from a location no other machine occupies. When its power finally fails and its instruments go silent, that stream of data will end, and there is currently nothing in development to replace it. The case for catching or following Voyager 1 is not sentimental, it is scientific. The region of space it occupies is one of the least understood environments in astrophysics, and Voyager barely scratched the surface before its instruments began failing. This crossing also matters for the catch-up problem because it illustrates a point that many people misunderstand. Voyager 1 did not leave the solar system. The solar system extends far beyond the heliosphere. The Oort cloud, a vast shell of icy bodies gravitationally bound to the Sun, stretches outward to perhaps 100,000 astronomical units. Voyager 1, at 163 astronomical units, has barely scratched the inner edge of this region. It will take roughly 300 years for the spacecraft to reach the inner boundary of the Oort cloud, and another 30,000 years to pass through it entirely. Even after it leaves the heliosphere, Voyager 1 remains gravitationally tied to the Sun. It is still orbiting, technically. Its orbit is simply so large and so elongated, a hyperbolic trajectory that will never curve back, that it looks from our perspective like a straight line into darkness. But the Sun's gravity is still tugging at it, still gently decelerating it by a vanishingly small amount each day. Over millions of years, that deceleration will reduce Voyager 1's speed by roughly a fraction of a kilometre per second. Not enough to stop it. Not enough to change the story, just enough to remind us that even at 15 billion miles, the Sun has not entirely let go. All of this builds toward a fact that sounds simple but carries enormous weight. Voyager 1 is the fastest object humanity has ever sent on an outbound trajectory from the Sun. Not the fastest spacecraft in general. The Parker Solar Probe, diving close to the Sun on a tight elliptical orbit, has reached speeds of 192 kilometers per second, more than 11 times Voyager 1's velocity. But Parker is not going anywhere. It is falling toward the Sun, swinging around at tremendous speed and climbing back outward, only to fall inward again. Its velocity is borrowed from the Sun's gravity well and given back on every orbit. Parker will never leave the solar system. Its blazing speed is a product of proximity, not escape. New Horizons, launched in January of 2006, left Earth faster than any spacecraft in history, flung away at roughly 16 kilometers per second by the most powerful upper stage combination ever used for a planetary mission. But New Horizons received only a modest gravity assist from Jupiter, adding roughly 4 kilometers per second. It never visited Saturn, Uranus, or Neptune. After its flyby of Pluto in 2015, it continued outward at approximately 14 kilometers per second. That is slower than Voyager 1. Despite being launched 29 years later with better technology and a more powerful rocket, New Horizons will never catch Voyager 1. It will never even narrow the gap. Voyager 1 is pulling away from New Horizons at roughly 3 kilometers per second, every second, forever. The newer, more modern spacecraft will spend eternity falling behind the older one. Pioneer 10 and Pioneer 11, launched in 1972 and 1973, were the first spacecraft to fly past Jupiter and Saturn. They are also on escape trajectories, heading out of the solar system in different directions. But both Pioneers travel slower than Voyager 1. Pioneer 10 moves at roughly 12 kilometers per second relative to the Sun. Pioneer 11 is slightly slower still. Neither will ever catch Voyager 1, and both lost contact with Earth years ago. Their transmitters too weak, and their power supplies too depleted to be heard across the growing distance. The result is a leaderboard that has not changed in decades. Voyager 1 is the fastest and farthest outbound spacecraft in existence, and nothing launched since 1977 has overtaken it. Nothing currently under construction will overtake it. The gap between Voyager 1 and every other outbound spacecraft is growing, not shrinking, and has been growing continuously for more than 40 years. This fact is both inspiring and deeply uncomfortable. It means that the pinnacle of humanity's outbound velocity was achieved not by a modern supercomputer-guided mission, but by a spacecraft designed with 1970s technology, carrying instruments that process 8,000 computer instructions per second, a processing speed roughly 2 million times slower than a modern smartphone. Voyager 1 does not owe its record to advanced engineering. It owes its record to a planetary alignment that will not repeat for another century and a half, and to the decision to aim for Titan instead of Uranus, which bent its trajectory just right to extract maximum speed from Saturn's gravity. No one at NASA in 1977 expected the spacecraft to last more than a decade. No one designed it to become humanity's farthest artifact. The mission was supposed to be over by 1981. Everything since then has been an improvisation, a slow-motion miracle of engineering endurance that has lasted 45 years longer than planned. Here is why all of this matters for the question of catching it. The challenge is not simply to build a faster spacecraft. Faster spacecraft exist conceptually. Faster speeds have been achieved in controlled environments close to the Sun. The challenge is that Voyager 1 has been accumulating distance at 38,000 miles per hour for nearly 50 years. It has a head start of more than 15 billion miles, and it is still moving. A faster spacecraft launched today does not start at Voyager 1's position. It starts at Earth. It must cross the entire distance Voyager 1 has already covered, and then continue gaining on it mile by mile, while Voyager 1 keeps adding to its lead during every single hour of the pursuit. Imagine two runners on a road. The first runner left the starting line 49 years ago and has been jogging at a steady pace ever since. The second runner is faster, perhaps twice as fast, but the second runner is still standing at the starting line, tying their shoes. The first runner is not waiting. Every minute the second runner spends preparing, the first runner adds another fraction of a mile to a lead that is already enormous. When the second runner finally begins, they do not simply need to be faster. They need to be faster for long enough to erase 49 years of accumulated distance, while the first runner continues to extend it. The math is not trivial, and in space the road is not straight. It bends through 3 dimensions along trajectories shaped by gravity, launch windows, and orbital mechanics. This is the true nature of the catch-up problem. It is not a speed problem alone. It is a speed plus time plus geometry problem, and the time component is what makes it so punishing. Every year humanity delays, Voyager 1 adds another 3.5 astronomical units to its lead. If a mission launched in 2036, Voyager 1 would be roughly 200 astronomical units away by the time the pursuer left Earth. If a mission launched in 2050, it would be roughly 250. The target keeps receding, and the closing distance keeps growing, and the mission duration stretches longer with every decade of inaction. And there is another dimension to this problem that almost no one considers. Voyager 1 is not heading in a convenient direction. Its trajectory, bent upward by the Titan flyby, aims 35 degrees above the ecliptic plane, where all the planets orbit. A spacecraft launching from Earth departs from within that plane. To match Voyager 1's path, a pursuer must not only accelerate to a higher speed, but also change its orbital inclination by 35 degrees, a maneuver that requires enormous amounts of energy. Inclination changes are among the most expensive operations in orbital mechanics. They demand fuel or gravity assists from planets that happen to sit in the right positions, or both. Matching Voyager 1's trajectory is not like driving down the same highway in the same direction. It is like driving down a highway that forks upward into the sky at a steep angle, and you need to leave the flat road and follow it. The combined effect of distance, speed, direction, and time creates a challenge that is qualitatively different from any other mission humanity has ever flown. We have sent spacecraft to every planet in the solar system. We have landed on Mars, orbited Jupiter, crashed a probe into Saturn's atmosphere, flown through the rings of Saturn, and photographed Pluto up close. But every one of those missions targeted an object whose position was known, whose trajectory was predictable, and whose distance was reachable within a span of years. not decades. Catching Voyager 1 would be the first time we attempted to intercept our own spacecraft in the void between stars. And the void is not empty. It is enormous. It is featureless. It offers no gravitational handholds, no landmarks, no course corrections beyond what the pursuer carries in its own fuel tanks. Voyager 1 does not know it is being discussed. It has no awareness, no intent, no destination. It is a collection of aluminum, silicon, plutonium, and magnetized tape, tumbling through darkness at 17 kilometers per second, faithfully pointing its antenna toward a pale dot of light that grows fainter every year. It carries a golden record encoded with sounds and images of Earth, a message for anyone or anything that might find it in the distant future. But the record is not the point of this story. The point is the distance. The point is the speed. The point is that every hour you spend listening to these words, Voyager 1 moves another 61,000 kilometers farther from everything you have ever known. And the question remains, hanging in the dark like the spacecraft itself. Could we close that gap? Could we build something fast enough, aim it precisely enough, and sustain it long enough to run Voyager 1 down? The answer begins with a deeper look at speed, and the uncomfortable discovery that the fastest machines humanity has ever built would fail completely at this task. The most common response people have when they hear about the challenge of catching Voyager 1 is to mention the Parker Solar Probe. It seems like an obvious solution. Parker holds the record for the fastest speed ever achieved by a human-made object. On December 24th, 2024, during its closest approach to the Sun, the spacecraft reached approximately 192 kilometers per second. That is roughly 692,000 kilometers per hour, or about 430,000 miles per hour. At that velocity, you could travel from New York to Los Angeles in about 20 seconds. You could reach the moon in roughly half an hour. The number sounds like it should solve everything. Voyager 1 moves at 17 kilometers per second. Parker moves at 192. The faster spacecraft should catch the slower one with ease. But this reasoning contains a fundamental misunderstanding of how speed works in space. And that misunderstanding reveals why catching Voyager 1 is so much harder than intuition suggests. Parker's solar probe is fast because it is falling. Not metaphorically, not poetically. It is literally falling toward the Sun on a highly elongated elliptical orbit, and like any falling object, it accelerates as it drops deeper into the gravitational well. Think of a ball rolling down the inside of a bowl. At the bottom of the bowl moves at its maximum speed, but then it climbs the other side, slowing down as gravity pulls it back. It reaches the rim, momentarily stops, and rolls back down again. Parker does exactly this, except the bowl is the Sun's gravitational field and the rim is the far end of its orbit near Venus. Every time Parker swings close to the Sun, it speeds up enormously. Every time it climbs back outward, it slows back down. Its peak velocity is a temporary condition, not a sustained cruise speed. Within hours of reaching 192 kilometers per second, Parker is already decelerating, giving back the speed it borrowed from the Sun's gravity. This is the critical distinction that most discussions of spacecraft speed ignore entirely. There is a difference between orbital speed and escape speed. Orbital speed is the velocity an object achieves while moving within a gravitational field, and it depends almost entirely on how deep into that field the object is. The closer you are to the Sun, the faster you orbit. Mercury moves faster than Earth. Earth moves faster than Mars. The Parker Solar Probe, diving to within 6 million kilometers of the Sun's surface, achieves speeds that dwarf anything in the outer solar system. But none of that speed helps it leave. To escape the Sun's gravity from Parker's closest approach point, a spacecraft would need a velocity well above the local escape speed, and it would need to apply that velocity in the right direction, radially outward, not along the orbital path. Parker's engines are not capable of that. Its mission was never designed for that. The spacecraft will continue looping around the Sun on its elliptical track until its fuel runs out, its heat shield fails, or its mission concludes. It will never leave the inner solar system. Imagine a car driving laps on a circular racetrack at 200 miles per hour. Someone standing outside the track points at the speedometer and says the car should be able to reach a city 500 miles north. But the car is not heading north. It is going in circles. Its speed is real, but its direction never carries it away from the track. To reach that distant city, the car would need to exit the track, merge onto a highway, and sustain a high speed in a straight line for hours. The racetrack speed and the highway speed are different problems entirely. Parker Solar Probe is on the racetrack. Voyager 1 is on the highway. Comparing their speedometers tells you almost nothing about which one can go farther. The same misunderstanding applies more subtly to the Helios 2 spacecraft, which held the previous speed record before Parker. Launched in 1976, Helios 2 reached approximately 70 kilometers per second during its perihelion passage. That was the fastest any human-made object had ever moved at the time, and it retained that record for over 40 years. But Helios 2 was also a solar orbiter. It never left the inner solar system. It was designed to study the sun from close range, not to escape outward. Its impressive speed existed only within the sun's deep gravitational well, and it meant nothing for interstellar travel. The confusion between these types of speed has real consequences for how the public understands space exploration. When headlines announce that the Parker Solar Probe is the fastest spacecraft ever built, most people assume this means it could reach distant destinations faster than anything else. It cannot. The speed that matters for catching Voyager 1 is not peak orbital velocity near the Sun. It is outbound cruise velocity far from the Sun, where the gravitational field is weak and a spacecraft must rely on whatever momentum it carried out of the inner solar system. By that measure, the rankings change completely. Parker Solar Probe's effective outbound speed is 0. It is not going outbound. It is staying in the Sun's neighborhood. Helios 2 had an effective outbound speed of 0 for the same reason. Even the fastest object ever built by human hands cannot chase Voyager 1, because speed without direction is merely spectacle. This is where New Horizons enters the story, and where the illusion becomes even more uncomfortable. New Horizons was launched on January 19, 2006, aboard an Atlas V rocket with 5 solid rocket boosters and a Star 48B upper stage. It left Earth's gravitational influence at approximately 16.26 kilometers per second, faster than any spacecraft had ever departed Earth. It crossed the Moon's orbit in roughly 9 hours, a journey that took Apollo astronauts 3 days. In terms of launch energy, New Horizons was genuinely the most powerful departure ever achieved from our planet. But launch speed and cruise speed are different things. After leaving Earth, New Horizons entered a heliocentric orbit heading toward Jupiter. It arrived at Jupiter in February of 2007 and received a gravity assist that added roughly 4 kilometers per second to its velocity. That boost bent its trajectory and sent it toward Pluto. After the Jupiter flyby, New Horizons began the long coast outward, and the Sun's gravity started pulling it back, decelerating it gradually, just as it decelerates every outbound spacecraft. By the time New Horizons reached Pluto in July of 2015, it was moving at approximately 14 kilometers per second relative to the Sun. After passing Pluto and its encounter with the Kuiper Belt object, Arrokoth, in 2019, New Horizons continued outward at roughly the same speed, a speed that will continue dropping slightly over the coming centuries, as the Sun's gravity weakens but never fully disappears. 14 kilometers per second, that is New Horizons' cruise speed into the outer solar system. Compare that to Voyager 1's 17 kilometers per second. The spacecraft launched 29 years later, with better technology, a more powerful rocket, and decades of accumulated knowledge in trajectory design, and it is traveling 3 kilometers per second slower than the machine it would need to catch. New Horizons will never overtake Voyager 1. Not in 100 years, not in 1,000, not ever. The gap between them is widening at roughly 3 kilometers per second, which amounts to about 95 million kilometers per year. Each year, Voyager 1 pulls roughly 95 million kilometers further ahead. New Horizons is not chasing Voyager 1. It is falling behind it, and the two spacecraft are not even heading in the same direction. Voyager 1 climbs northward above the ecliptic plane at 35 degrees, heading toward the constellation Ophiuchus. New Horizons moves along a flatter trajectory, closer to the ecliptic, heading in a different direction entirely. Even if New Horizons was somehow faster, it would be flying the wrong way. The paths diverge. The gap is not merely a matter of distance along the same road, it is a matter of distance across three-dimensional space, with the two spacecraft heading on completely separate headings. This comparison reveals a deeper truth about the catch-up problem. The issue is not that humanity lacks fast spacecraft. The issue is that none of the fast spacecraft we have ever launched are heading where Voyager 1 is heading, at the speed Voyager 1 is heading there, with the trajectory Voyager 1 follows. Speed is only one component of an intercept. Direction is another. Timing is another. And all three must be solved simultaneously for a rendezvous to work. Consider what an intercept actually requires. It is not enough to reach the point in space where Voyager 1 sits right now. By the time any new spacecraft crosses 15 billion miles, Voyager 1 will no longer be at that point. It will be millions or billions of miles farther along its trajectory, depending on how long the pursuit takes. The pursuing spacecraft must aim not at where Voyager 1 is today, but at where Voyager 1 will be years or decades in the future. This is the same principle that a quarterback uses when throwing a football to a moving receiver. You do not throw to where the receiver stands when you release the ball. You throw to where the receiver will be when the ball arrives. Except in this case, the receiver is running at 38,000 miles per hour, the football takes years to reach the catch point, and the field is three-dimensional. This targeting challenge means that a faster spacecraft does not simply fly in a straight line toward Voyager 1. It follows a calculated intercept trajectory that accounts for both its own velocity and Voyager 1's velocity over the entire flight time. The math requires knowing the exact positions and velocities of both objects at every moment. It requires computing a path that closes the angular separation between the two trajectories while simultaneously closing the distance. If the pursuer is much faster than Voyager 1, the intercept geometry becomes more forgiving because the closing speed is high and the flight time is shorter, giving Voyager less time to move. If the pursuer is only slightly faster, the geometry becomes punishing. The flight time stretches into decades. Voyager keeps moving for all of those decades, and even small navigational errors compound into misses measured in millions of kilometers. This distinction between reaching a distance and intercepting an object is one of the most misunderstood aspects of the problem. A spacecraft that could travel at, say, 25 kilometers per second, roughly 50% faster than Voyager 1, would eventually catch it. But the word eventually does enormous work in that sentence. Let me walk through the numbers slowly, because the scale of the pursuit only becomes real when you watch it unfold year by year. If such a spacecraft launched in 2036, when Voyager 1 would be roughly 200 astronomical units from the Sun, the closing speed between them would be about 8 kilometers per second. That sounds meaningful until you translate it into distance. 8 kilometers per second is roughly 1.7 astronomical units per year of closing. In the first decade of pursuit, by 2046, the chaser has narrowed the gap by roughly 17 astronomical units. But during that same decade, Voyager 1 has moved 35 astronomical units farther away. The pursuer is faster, so the gap shrinks, but it shrinks slowly. After 10 years of flight, the remaining distance is still roughly 183 astronomical units. The chaser has been flying for a decade and has closed less than 10% of the original gap. By 2056, after 20 years, the gap has narrowed to about 166 astronomical units. 20 years of continuous flight, 20 years of maintaining power systems and communication links, and navigational precision across distances that dwarf anything humanity has ever attempted. And the pursuer is still farther from Voyager 1 than Voyager 1 currently is from the Sun. The mission is not even halfway done. The engineers who launched it are retiring or dying. A new generation has inherited a spacecraft they did not build, chasing a target they have never known in any context other than this pursuit. By 2066, 30 years in, the gap drops to about 149 astronomical units. By 2076, 40 years, roughly 132 astronomical units remain. By 2086, 50 years, the distance is about 115 astronomical units. After half a century of flight, the pursuer is still roughly 3 times farther from Voyager 1 than Pluto is from the Sun. The pursuit continues, year after year, decade after decade. The gap shrinks by the same increment each year, but the years pile up in a way that defies human attention spans. The spacecraft would finally catch Voyager 1 around 2154, roughly 118 years after launch. 118 years. That is longer than any human being has ever lived. Longer than any space agency has ever existed. Longer than the entire history of powered flight. From the Wright brothers to the present day, the spacecraft would need to function autonomously for a duration that exceeds the lifespan of the institutions that built it, the governments that funded it, and possibly the political systems that authorized it. And throughout all of those years, Voyager 1 simply keeps jogging along at 17 kilometers per second, indifferent to the pursuit, unaware it is being chased, growing older and quieter in the dark. Increasing the pursuer's speed helps dramatically. A spacecraft traveling at 35 kilometers per second, roughly double Voyager 1's velocity, would close the gap at 18 kilometers per second. The same 200 astronomical unit head start would take roughly 53 years to erase. Still an entire human lifetime, but conceivable. At 50 kilometers per second, nearly 3 times Voyager 1's speed, the pursuit time drops to about 28 years, more manageable, but each of these speeds represents a staggering engineering challenge. No spacecraft currently in development can sustain 35 kilometers per second on an outbound solar system escape trajectory, let alone 50. The fastest outbound spacecraft ever launched, Voyager 1 itself, manages only 17. Doubling or tripling that number requires propulsion systems that either do not exist yet or exist only as concepts on paper. The reason doubling or tripling the speed is so difficult comes down to a relationship that governs every rocket ever built and ever will be built. Kinetic energy increases with the square of velocity. Doubling your speed does not require double the energy. It requires 4 times the energy. Tripling your speed requires 9 times the energy. This is not an engineering limitation. It is physics. No amount of cleverness or funding can change the exponent. But the problem compounds further because of how rockets work. A rocket must carry its own fuel. That fuel has mass. Accelerating that fuel mass requires more fuel. Accelerating that additional fuel requires still more fuel. This cascading relationship is described by the Tsiolkovsky rocket equation, and it is exponential. A spacecraft that needs to reach 35 kilometers per second using chemical propulsion must carry fuel that outweighs its payload by a staggering ratio. For a high-performance chemical rocket with an exhaust velocity of roughly 4.5 kilometers per second, achieving 35 kilometers per second of velocity change requires a mass ratio of roughly 2,400 to 1. That means for every kilogram of spacecraft that arrives at Voyager 1, you need 2,400 kilograms of fuel at launch. A modest 500 kilogram probe would require a launch mass of 1.2 million kilograms, roughly the same as 30 fully loaded semi-trucks stacked into a single rocket. That mass must be lifted off Earth, assembled into a functional vehicle, and pointed in the right direction without error. At 50 kilometers per second, the numbers become absurd. The mass ratio climbs to roughly 66,000 to 1. A 500 kilogram probe would need 33 million kilograms of propellant at launch. That is roughly a third the weight of a modern aircraft carrier, just to chase one small probe. No rocket in history, no rocket currently planned, could lift a fraction of that mass to orbit, let alone assemble it into a functioning interstellar chase vehicle. The tyranny of the rocket equation does not negotiate. You can stage the rocket, splitting it into sections that are discarded as they empty, and that helps. You can use gravity assists from Jupiter to add speed without fuel. That helps too. But every technique has limits, and those limits fall far short of what a brute force chemical intercept would demand. This is why the problem cannot be solved by simply building a bigger rocket. There is no economically or physically plausible chemical rocket that can reach 50 kilometers per second outbound. There is barely a plausible one that can reach 35. The exponential scaling of fuel requirements creates a wall that cannot be climbed by incremental improvement. Crossing it requires either fundamentally different propulsion, like nuclear thermal or nuclear electric engines that extract more velocity from each kilogram of fuel, or fundamentally different energy sources, like solar gravity assists or external laser propulsion, that do not require the spacecraft to carry its own energy supply. Each of those alternatives comes with its own set of complications, which is precisely why no Voyager intercept mission has ever left the drawing board. There is another layer to the speed problem that makes the challenge even more severe. The speed figures people commonly cite for outbound spacecraft are heliocentric velocities measured from the Sun's frame of reference. But when a spacecraft launches from Earth, its initial velocity includes Earth's own orbital speed, roughly 30 kilometers per second around the Sun. A spacecraft launched in the same direction as Earth's motion starts with that velocity as a gift. A spacecraft launched in the opposite direction must overcome it. Voyager 1's 17 kilometers per second is a heliocentric speed that already subtracts the energy lost climbing out of the Sun's gravity well. The launch energy required to achieve 17 kilometers per second at Voyager 1's current distance from the Sun was far higher at the point of departure. To launch a spacecraft that arrives at deep interstellar distances moving at 35 kilometers per second, you need an enormous amount of energy at departure, energy that translates to massive rockets, multiple gravity assists, or propulsion technologies beyond anything currently operational. This is why the fastest spacecraft ever built tells us almost nothing about whether we can catch Voyager 1. Parker Solar Probe's 192 kilometers per second is a number earned in the Sun's basement, deep in the gravitational well, moving sideways, going nowhere outward. New Horizons' 16 km per second launch speed was the most energetic departure in history, and it still produced a cruise velocity 3 km per second short of Voyager 1's. The gap between what we can achieve in close solar orbit and what we need for an interstellar intercept is enormous. It is not a gap that better rockets alone can close. It is a gap that requires rethinking how we design missions entirely. And the geometry remains relentless. Even a hypothetical spacecraft fast enough to close on Voyager 1 must contend with the directional mismatch. Voyager 1's trajectory, angled steeply above the ecliptic, is not aligned with any convenient planetary flyby path. A pursuer launching from Earth cannot easily use Jupiter or Saturn to slingshot itself onto Voyager 1's heading, because those planets orbit in the ecliptic plane, and Voyager 1 does not. Matching the inclination requires either a dedicated propulsive maneuver, which costs fuel and reduces final speed, or a complex multi-planet flyby sequence that may not be available for decades due to planetary alignment constraints. The alignment problem echoes the original Grand Tour window that made Voyager possible in the first place. That alignment occurs roughly every 176 years. Future intercept missions would not need that exact alignment, but they would need their own favourable launch windows, moments when Earth, Jupiter, and the Sun are positioned to offer the best combination of gravity assists and trajectory angles. Miss the window and you wait years for the next one. Miss several windows and the head start grows by billions of additional kilometres. All of this paints a portrait of a problem far more layered than a simple speed comparison. The public sees a headline saying Parker Solar Probe travels at 430,000 miles per hour, and naturally wonders why we cannot just point that speed at Voyager 1. The answer is that speed in space is contextual. It depends on where you are, which direction you are heading, what gravitational field you are embedded in, and whether your velocity carries you toward your target or merely around a central body. The speed that matters for catching Voyager 1 is not the peak velocity of any spacecraft on any trajectory. It is the sustained outbound velocity of a spacecraft, specifically aimed at Voyager 1's future position, launched on a trajectory that matches its angular heading, with enough energy to close a gap that has been growing for half a century. No such spacecraft exists today. None is under construction. None is funded. The fastest outbound machine in human history is still the one we are trying to catch, and it achieved its speed through a trick of planetary alignment that will not be available again for more than 100 years. But the situation is not entirely hopeless. Concepts exist. Plans have been sketched. Engineers at some of the most capable laboratories in the world have studied exactly what a Voyager intercept mission would demand. What they found is that the answer does not lie in exotic propulsion or science fiction technology. It lies in clever mission design, ruthless engineering discipline, and a willingness to commit to a flight that would outlast the careers of everyone who approved it. The question is what that flight would actually look like. If catching Voyager 1 was simply a matter of raw velocity, someone would have proposed a credible mission decades ago. The reason no agency has ever funded or approved such a mission is not a lack of ambition. It is that the engineering requirements land in an uncomfortable gap between what is currently operational and what remains speculative. The machines that could theoretically catch Voyager 1 either do not exist, carry payloads too small to matter, or demand mission durations that outlast the institutions responsible for flying them. Understanding why requires walking through the actual menu of options, from the pragmatic to the exotic, and seeing where each one breaks down. The most realistic proposal on the table is not a Voyager intercept mission at all. It is the Interstellar Probe concept, developed by the Johns Hopkins Applied Physics Laboratory in collaboration with NASA. The study, led by principal investigator Ralph McNutt and supported by a nearly 500-page mission concept report published in 2021, proposes a dedicated spacecraft designed to explore the boundary between the heliosphere and interstellar space, the same region that Voyager 1 stumbled into without the right instruments to study it properly. The baseline design calls for a launch in the mid-2030s, with 2036 used as the reference year. The spacecraft would weigh roughly 860 kilograms, comparable to the Voyager probes, and would launch on a heavy-lift rocket such as the Space Launch System. After departure from Earth, it would fly past Jupiter for a gravity assist, picking up speed and redirecting its trajectory outward. After the Jupiter flyby, the Interstellar Probe would cruise at approximately 7 astronomical units per year. That is roughly double Voyager 1's rate of 3.5 astronomical units per year. At 7 astronomical units per year, the Interstellar Probe would be genuinely fast. It would reach the heliopause in roughly 15 years, compared to the 35 years Voyager 1 needed. It would pass 200 astronomical units within about 30 years. And crucially, because it moves at twice Voyager 1's speed, it would slowly close the gap. The closing rate would be approximately 3.5 astronomical units per year, meaning the Interstellar Probe would gain about 525 million kilometers on Voyager 1 each year. That sounds fast until you realize how large the head start is. If the Interstellar Probe launched in 2036, Voyager 1 would be roughly 200 astronomical units from the Sun at that point. Erasing 200 astronomical units at a closing rate of 3.5 astronomical units per year would take approximately 57 years. The Interstellar Probe would not catch Voyager 1 until roughly 2093, nearly the end of the 21st century. 57 years. That is the most optimistic timeline using the most realistic propulsion concept currently studied in detail, and that timeline assumes everything goes perfectly. No launch delays, no trajectory errors, no system failures across 6 decades of deep space flight. For context, the longest operating deep space mission in history is Voyager itself, approaching 50 years. Asking a new spacecraft to function reliably for 60 years in interstellar space, far from any possibility of repair, is not a trivial engineering demand. It requires power sources that last, computers that do not degrade, communication systems that remain functional across distances approaching 300 astronomical units. Every component must be designed for a mission duration that spans the careers of 3 or 4 generations of engineers. And there is a critical caveat. The Interstellar Probe was never designed to intercept Voyager 1. It was designed to explore interstellar space along its own optimized trajectory, which would aim in a different direction than Voyager 1's path. To actually catch Voyager 1, the mission would need to be redesigned from the ground up, with a trajectory specifically bent to match Voyager 1's heading of 35 degrees above the ecliptic toward the constellation Ophiuchus. That redesign would cost energy. Matching the inclination requires a propulsive maneuver or a different gravity assist geometry at Jupiter, either of which would reduce the final cruise speed below 7 astronomical units per year. The actual pursuit time would likely be longer than 57 years, possibly much longer. The Interstellar Probe study demonstrates that overtaking Voyager 1 before the 22nd century is theoretically possible using existing chemical propulsion and proven gravity assist techniques. What it does not demonstrate is that anyone could do it affordably, reliably, or with a spacecraft aimed at the right patch of sky. There is one technique that could dramatically increase the departure speed without requiring exotic propulsion technology. It is called the Oberth maneuver, named after the physicist Hermann Oberth, who documented the principle in 1929. The concept is elegant and counterintuitive. A spacecraft first dives deep into a gravitational well, falling toward a massive body like the Sun on a deliberately plunging trajectory. At the closest point of approach, the perihelion, it fires its engines. The key insight is that a propulsive burn performed deep in a gravity well produces a much larger change in total orbital energy than the same burn performed far from any gravitational body. The deeper you fall before you fire, the more energy your fuel gives you. It is like running downhill before jumping. The hill adds to your speed, and the jump at the bottom carries you farther than a standing jump on flat ground ever could. Applied to the Sun, an Oberth maneuver could work like this. A spacecraft launches from Earth and uses planetary flybys to set up a trajectory that plunges close to the Sun, perhaps within 10 or 15 solar radii. At perihelion, it fires a large solid or liquid rocket motor, performing a burn that adds perhaps 6 to 8 kilometers per second of delta V. Because this burn happens deep in the Sun's gravitational well, the resulting boost to the spacecraft's outbound asymptotic velocity is magnified enormously. Depending on the exact perihelion distance and the size of the burn, the spacecraft could depart the inner solar system at speeds exceeding 10 or even 15 astronomical units per year. At 15 astronomical units per year, the closing rate on Voyager 1 would be roughly 11.5 astronomical units per year, cutting the pursuit time to under 20 years from the moment the burn is complete. This sounds transformative, and in many ways it is, but the Oberth maneuver near the Sun carries terrifying engineering challenges. Consider what the spacecraft would physically experience. As it falls inward from Earth's orbital distance toward a perihelion of 10 solar radii, roughly 7 million kilometers from the Sun's surface, the solar flux increases by a factor of more than 400. The spacecraft's sun-facing side reaches temperatures that would soften steel and ignite most organic materials. The heat shield required is not merely a passive barrier. It must protect a fully fueled rocket motor, its propellant tanks, its plumbing, its ignition system, and the payload behind it, all of which must remain cold enough to function during and immediately after the burn. The shield must survive not only radiative heating from the Sun, but also the mechanical stresses of a rocket firing while the spacecraft is being roasted. One crack, one thermal expansion joint that fails, one seal that softens, and the entire mission is lost in a flash of vaporized propellant 7 million kilometers from the nearest repair shop. The Parker Solar Probe survives close solar passes because it hides behind a carbon composite heat shield and makes brief transits through the danger zone on an elliptical orbit. But Parker carries no large rocket motor, it carries no volatile propellants. Its instruments are miniaturized and designed to operate in shadow. A spacecraft performing an Oberth maneuver would be a fundamentally different machine, a combination of heat shield, heavy rocket, and deep space probe that has never been built and never been tested. The engineering is plausible on paper, the physics works, but the gap between thermal analysis on a computer screen and a functioning vehicle diving toward the Sun with a fully loaded engine is the kind of gap that can swallow missions whole. Several studies, including analyses associated with the Interstellar Probe concept, have explored the Oberth maneuver as a way to reach high, outbound velocities. The results are promising but cautious. The technique could push a spacecraft to speeds that make a Voyager intercept feasible within decades rather than centuries. But the thermal protection requirements, the precision of the solar flyby, and the risk of catastrophic failure during the burn all place it firmly in the category of high-reward, high-risk architecture. No space agency has approved or funded a solar Oberth mission. The concept exists in the space between proven technology and engineering ambition, waiting for a program willing to take the leap. Nuclear propulsion represents another path, one that has been studied intermittently for decades without reaching operational status. The basic idea is to use a nuclear reactor to heat propellant to extremely high temperatures and expel it at velocities far exceeding what chemical rockets can achieve. The measure of propulsion efficiency is specific impulse, essentially how much thrust you get per unit of fuel. Chemical rockets top out at a specific impulse of roughly 450 seconds. Nuclear thermal rockets can theoretically achieve 800 to 900 seconds, roughly double. This means a nuclear-powered spacecraft can either go faster on the same amount of fuel or carry less fuel for the same speed. Either way, the mission gains substantial performance. This is not a new idea. In the 1960s, NASA and the Atomic Energy Commission jointly developed and tested a series of nuclear rocket engines under a program called NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. NERVA engines were built, mounted on test stands in the Nevada desert, and fired repeatedly. They worked. They achieved specific impulses above 800 seconds. They demonstrated that a nuclear thermal engine could produce thrust reliably and could be throttled and restarted. The technology was real, tested, and ready for the next phase of development. And then it was cancelled. The political appetite for nuclear rockets evaporated as the Apollo program wound down and budgets shrank. NERVA's engines were mothballed. The test stands were dismantled. Decades of accumulated engineering knowledge were shelved, and nuclear propulsion entered a long hibernation from which it has never fully emerged. NASA's DRACO program, a collaboration with the Defense Advanced Research Projects Agency, was intended to revive nuclear thermal propulsion and demonstrate it in space. The program aimed to build and fly a nuclear thermal rocket engine by the mid-2020s. Had it succeeded and led to operational systems, nuclear thermal propulsion could have enabled faster missions to Mars and, eventually, to the outer solar system and beyond. However, the program was cancelled, leaving nuclear thermal propulsion without a near-term flight demonstration for the second time in its history. The technology remains theoretically sound. The physics works. The engineering has been studied extensively since the 1960s, but without a flight-proven system, nuclear thermal propulsion cannot be counted on for a near-term Voyager intercept mission. It remains a future possibility rather than a present capability. The irony is bitter. We had working nuclear rocket engines more than 50 years ago. We chose not to use them. And now, when a mission exists that would benefit enormously from that technology, we would need to rebuild the capability from scratch. Nuclear electric propulsion offers a different approach. Instead of heating propellant directly with a reactor, a nuclear electric system generates electricity from a reactor and uses that electricity to power ion thrusters. Ion thrusters produce very low thrust, but operate at extremely high specific impulse, thousands of seconds rather than hundreds. They accelerate slowly but continuously over months or years, eventually building up tremendous velocity. A nuclear electric spacecraft could theoretically achieve outbound speeds of 10 to 15 astronomical units per year if given enough time to accelerate. But the acceleration phase might last years, during which the spacecraft covers a large portion of the inner solar system. The trajectory design becomes complex, and the low thrust means the spacecraft cannot perform sharp maneuvers. It must follow a gradual spiral outward, gaining speed slowly, before finally breaking free on a hyperbolic escape trajectory. This approach could be powerful for a long-duration mission to interstellar space. It is less well suited to a precise intercept of a specific moving target like Voyager 1, because the gradual acceleration and spiral trajectory make it difficult to fine-tune the arrival geometry. A nuclear electric spacecraft aimed at Voyager 1 would need to balance continuous acceleration with trajectory corrections, navigating a curved path through the solar system toward a target that is simultaneously speeding away along a different heading. The flight dynamics are solvable but challenging, and no nuclear electric mission of this scale has ever been flown. The closest analogue is NASA's Dawn mission, which used ion propulsion to visit 2 asteroids in the main belt. Dawn demonstrated that electric propulsion works in deep space, but its velocities and distances were trivial compared to what a Voyager intercept would require. At the other end of the spectrum sits Breakthrough Starshot, the most ambitious propulsion concept ever seriously proposed. Funded by Russian-Israeli billionaire Yuri Milner and announced in 2016 with the backing of the late Stephen Hawking, Breakthrough Starshot aims to accelerate a gram-scale spacecraft to 20% the speed of light using a ground-based laser array. The laser would shine on an ultra-thin reflective sail attached to a chip-sized payload, accelerating it from rest to roughly 60,000 kilometers per second in a matter of minutes. At that speed, the spacecraft could reach Alpha Centauri, the nearest star system to our Sun, at 4.37 light-years away, in approximately 20 years. 20% of the speed of light is not a small number. It is 60,000 kilometers per second. Voyager 1 moves at 17 kilometers per second. A Starshot sail moving at 60,000 kilometers per second would cross Voyager 1's distance in a matter of days, not decades. From a pure speed perspective, Starshot makes the intercept problem vanish entirely. But Starshot cannot catch Voyager 1. The reasons are fundamental and have nothing to do with speed. First, the payload mass. Breakthrough Starshot is designed around a spacecraft weighing roughly 1 gram. 1 gram! The entire probe, including its camera, communication system, navigation sensors, and power supply, must fit on a chip smaller than a postage stamp. This is not a spacecraft that can dock with anything, photograph anything at close range with high resolution, or carry instruments capable of meaningful scientific measurements during a fleeting passage. It is a proof-of-concept vehicle for interstellar flybys, not rendezvous missions. Second, Starshot cannot slow down. The laser propulsion system accelerates the sail during a brief burst near Earth. After that, the sail coasts at 20% of the speed of light, with no way to decelerate. There are no brakes, no reverse thrust, no retro rockets. The spacecraft would pass Voyager 1 at a relative velocity of roughly 59,983 kilometers per second. At that speed, the encounter would last a fraction of a second. Voyager 1 would be a blur if it were detectable at all. This is not an intercept, it is a bullet passing through a room. The two objects would share the same neighborhood for an instant too brief for any meaningful interaction. Third, Starshot does not exist yet. The laser array required to accelerate the sails would need to produce roughly 100 gigawatts of power, focused on a sail less than 5 meters across, with tracking precision sufficient to keep the beam on target during the entire acceleration phase. No such laser array has been built. The material science for the sail, which must survive intense laser flux without melting, is still in the laboratory stage. Experimental measurements of laser-induced sail motion have been demonstrated at Caltech, but the gap between a tabletop experiment and a functioning interstellar launch system is measured in decades of development and tens of billions of dollars. Breakthrough Starshot is not a near-term solution to catching Voyager 1. It is a long-term vision for interstellar exploration that, if realized, would make the Voyager catch-up problem irrelevant by making Voyager 1's speed look like a rounding error. But that future is decades away at minimum, and the specific problem of intercepting and rendezvousing with a 722-kilogram spacecraft moving at 17 kilometers per second along a specific trajectory requires capabilities that Starshot does not offer and was never intended to provide. What emerges from this survey of options is a sobering conclusion. The most plausible path to overtaking Voyager 1 is also the least glamorous. It does not involve nuclear reactors, laser sails, or relativistic velocities. It involves a large, carefully designed chemical propulsion spacecraft launched on a heavy-lift rocket aimed at Jupiter for a gravity assist, possibly incorporating a solar Oberth maneuver to boost its departure speed, and then coasting outward at 7 to 15 astronomical units per year on a trajectory painstakingly designed to converge with Voyager 1's path. The mission would last decades. Its success would depend on power systems that function for half a century or more, communication technology capable of maintaining contact at 300 or more astronomical units, and autonomous navigation software capable of correcting course without real-time ground control. The spacecraft would carry instruments designed to study interstellar space along the way, because no agency would fund a 60-year mission with the sole purpose of catching an old probe. The science must justify the journey. Voyager 1 would be a bonus, a target of opportunity along a route already scientifically compelling. But suppose the mission is approved. Suppose the spacecraft is built, launched, and performs flawlessly. Suppose it crosses 200 astronomical units and closes on Voyager 1's position after decades of flight. What happens then? What would an intercept actually look like? This is the question that almost every discussion of catching Voyager 1 ignores entirely, and it turns out to be one of the hardest parts of the problem. Catching Voyager 1 does not mean pulling up alongside it like one car overtaking another on a highway. In deep space, there is no road. There is no friction to match speeds. The pursuing spacecraft arrives at Voyager 1's vicinity moving at a different velocity on a converging trajectory, and the relative speed between the two objects determines what kind of encounter is possible. If the pursuer is travelling at 7 astronomical units per year and Voyager is travelling at 3.5, the closing speed at the moment of intercept is approximately 3.5 astronomical units per year. or roughly 16.5 kilometers per second. The pursuer would blow past Voyager 1 at 16.5 kilometers per second unless it carries enough fuel to decelerate and match Voyager's velocity. Matching velocity with Voyager 1 is an entirely separate propulsion problem from reaching it. The spacecraft must not only arrive at the same point in space at the same time, but must also slow down to 17 kilometers per second, traveling in the same direction at the same angle above the ecliptic. This requires a deceleration burn of roughly 16.5 kilometers per second, which demands enormous amounts of fuel or an exceptionally efficient propulsion system. Carrying that fuel from Earth adds mass to the pursuer, which in turn requires more fuel to accelerate it in the first place, which adds more mass, which requires more fuel. This is the tyranny of the rocket equation, the exponential relationship between payload mass and fuel mass that constrains every mission ever designed. A spacecraft that must both reach Voyager 1 and then match its velocity is a fundamentally heavier, more expensive, and more complex machine than one that merely needs to fly past it. If a pursuer cannot match velocity, the encounter becomes a flyby. The spacecraft streaks past Voyager 1 at thousands of miles per hour, photographing it as it passes, measuring its magnetic field, perhaps bouncing a radar signal off its hull to create a three-dimensional map. The encounter might last minutes or hours depending on the exact closing speed and the distance at closest approach. It would produce data, it would produce images, but it would not allow the pursuer to dock, to inspect, to touch. It would be a glimpse, not a reunion. And there is the question of finding Voyager 1 at all. At 300 astronomical units, the spacecraft is a 722-kilogram object in a volume of space so vast that even a small navigational error could place the pursuer millions of kilometers from the target. Voyager 1's position is known precisely today because we are still tracking it with the Deep Space Network. But by the time a pursuer arrives, the tracking data may be decades old, and any residual uncertainty in Voyager 1's trajectory will have compounded over the intervening years. The pursuer would need its own means of detecting and homing in on Voyager 1 during the final approach phase, either by picking up its radio signal, if it is still transmitting, or by imaging it against the star field using onboard cameras. At 300 astronomical units, Voyager 1 would appear as a faint dot reflecting starlight, indistinguishable from distant asteroids or cosmic ray hits on the camera sensor. Finding a small car-sized object in the darkness between stars requires navigational precision measured in fractions of an arc-second, sustained over decades of flight. And even this most plausible scenario remains unfunded. The Interstellar Probe concept report was published, the science case was presented, the technology was assessed as ready, but no budget line exists. No launch date has been approved, no hardware is being built. The study sits on a shelf alongside decades of other interstellar mission concepts, waiting for a political and financial commitment that has never materialized. Meanwhile, Voyager 1 adds another 3.5 astronomical units to its lead every year. Every year the decision is deferred, the pursuit grows longer, the mission grows harder, and the window narrows for catching the spacecraft while any of the engineers who designed it are still alive to see it overtaken. The honest summary of the intercept problem is this: catching Voyager 1 is not impossible. It is within the reach of technology that either exists today or could be developed within a decade. The propulsion is feasible. The trajectory design is understood. The engineering challenges are severe but not insurmountable. What is missing is not capability. What is missing is commitment. The willingness to fund a mission whose results will not arrive until the grandchildren of the people who approved it have grown old. The willingness to build a machine whose purpose will outlast every government, every budget cycle, and every political priority that exists at the moment of launch. Catching Voyager 1 requires thinking on a timescale that human institutions almost never operate on, and that may be the hardest part of the problem. Not the speed, not the distance, not the trajectory. The patience. What happens when you set aside the engineering and focus instead on the object itself reveals something even more difficult to confront. Voyager 1 is not just far away and fast. It is dying. Voyager 1 is dying the way all machines die when no one can reach them. Not in a single dramatic failure, not in a flash or an explosion, but slowly, one system at a time, growing quieter with each passing year. The spacecraft that crossed the heliopause that photographed the volcanoes of Io, that revealed the intricate braids of Saturn's rings, that captured the image of Earth as a pale blue pixel suspended in a sunbeam, is now shedding its senses one by one, like an aging explorer losing sight and hearing on a road that has no end. The power source is the clock that governs everything. Voyager 1 carries 3 radioisotope thermoelectric generators, devices that convert the heat produced by the natural decay of plutonium-238 into electricity. When the spacecraft launched in 1977, those generators produced roughly 470 watts of electrical power. That is less than the energy consumed by 5 household light bulbs. It was enough to run a suite of scientific instruments, a radio transmitter, heaters to keep critical components from freezing, computers to process commands and format data, and attitude control systems to keep the antenna pointed at Earth. Nearly 5 decades later, the plutonium has decayed to the point where the generators produce fewer than 220 watts. The output drops by approximately 4 watts every year, a decline that is governed by the half-life of plutonium-238, which is 87.7 years. This decay is not a malfunction, it is physics. It cannot be stopped, reversed, or slowed. The plutonium does not care about the mission. It follows its own atomic schedule, and the spacecraft must accommodate whatever power remains. For years, engineers at the Jet Propulsion Laboratory have been managing this decline with a kind of clinical tenderness. Each time the power drops below the level needed to operate all remaining systems, they face a choice. Which instrument do you turn off? Which heater do you sacrifice? Which piece of the spacecraft's awareness do you surrender in order to keep the rest alive a little longer? These decisions are not made lightly. Each instrument represents decades of scientific investment and provides data that no other machine in existence can replicate. Voyager 1 and its twin Voyager 2 are the only spacecraft operating in interstellar space. Every measurement they return is unique, irreplaceable, a first and possibly a last. The fragility of the connection was made painfully clear in late 2023 and early 2024 when Voyager 1 began transmitting nonsense. The data stream that had flowed reliably for more than 46 years suddenly turned into a repeating pattern of ones and zeros that contained no usable information. The telemetry was garbled. The science data was gone. The spacecraft was still alive, its carrier signal still detectable, but it had lost the ability to speak in any language Earth could understand. Engineers at the Jet Propulsion Laboratory spent months diagnosing the problem from a distance of more than 15 billion miles, working through a communication delay that meant every command took nearly 2 days to send and confirm. They eventually traced the fault to a single corrupted memory chip in the flight data subsystem, one of the spacecraft's aging computers. A section of the chip had failed, scrambling the code responsible for packaging telemetry data into a format the Deep Space Network could read. The fix was extraordinary. Engineers could not replace the chip. They could not reboot the system in any conventional sense. Instead, they devised a workaround that split the corrupted code into segments and relocated those segments to other areas of the spacecraft's memory, areas that still functioned but had not been designed for that purpose. The patched code had to be written, tested in simulation on Earth, transmitted across 15 billion miles, loaded into a 46-year-old computer with 8,000 instructions per second of processing power, and executed without error. If the patch failed, there was a real possibility that Voyager 1 would never produce usable data again. In April of 2024, the patch was uploaded. It worked. Voyager 1 began speaking clearly again. The engineers who pulled it off described the process with the understated precision characteristic of people who fix spacecraft for a living. But what they accomplished was closer to performing cardiac surgery on a patient in another country, using only a telegraph machine and a 48-hour postal delay. The patient survived, but the episode revealed how close Voyager 1 lives to the edge of failure at all times, and how thin the margin is between a functioning interstellar probe and a silent piece of drifting metal. On April 17th, 2026, that calculus forced another sacrifice. Engineers sent a command to shut down the low-energy charged particles instrument, a device that had been operating almost without interruption since launch. The command took nearly 23 hours to reach the spacecraft, traveling at the speed of light across 15 billion miles. The shutdown itself required approximately 3 hours and 15 minutes to execute. A small component, the instrument's scanning motor, was left energized at roughly half a watt to keep it warm enough for a potential restart, though no restart date has been set. The low-energy charged particles instrument had spent 49 years measuring ions, electrons, and cosmic rays. It helped scientists map the boundary between the heliosphere and interstellar space. It detected pressure fronts in the interstellar medium that no Earth-based telescope could observe. And now it is silent. The shutdown was triggered by an unexpected drop in power levels during a routine roll maneuver in late February of 2026. The dip brought Voyager 1 dangerously close to triggering its automatic undervoltage fault protection, a self-preservation mode that would have shut down critical systems autonomously and required a risky, multi-day recovery effort conducted across a 2-day communication delay. Rather than risk that cascading failure, engineers chose a controlled retreat. They turned off one instrument to preserve the others. Voyager 1 now operates with 2 functioning science instruments. One listens for plasma waves, detecting the faint oscillations of charged particles in the interstellar medium. The other measures magnetic fields, sensing the direction and strength of the magnetic environment between the stars. Together, they provide a narrow but invaluable window into a region of space that no other instrument can reach. Every bit of data they return travels 15 billion miles at the speed of light, arriving at Earth's deep space network antennas as a whisper so faint it borders on the theoretical limit of detection. And the engineers who receive it know that each transmission could be among the last. There is a plan to buy more time. Engineers have developed an approach they informally call the Big Bang, a coordinated swap of several powered components at once, trading older systems for lower power alternatives. The idea is to reconfigure Voyager 1's internal power distribution in a single, carefully sequenced operation, freeing up enough wattage to keep the remaining instruments running for additional months or possibly years. The procedure will be tested first on Voyager 2, which has slightly more power to spare and is closer to Earth, making it a safer test subject. Testing is planned for mid-2026. If the results are successful, the same procedure will be attempted on Voyager 1 no sooner than July. If it works, there is even a slim chance the low-energy charged particles instrument could be turned back on. But even the most optimistic projections converge on the same conclusion. Sometime in the late 2020s or early 2030s, Voyager 1 will no longer have enough power to operate any science instrument at all. The last sensor will go dark. The last data point will be recorded. The spacecraft will still be transmitting a carrier signal, a simple tone confirming that it is alive, but there will be nothing left to say. The stream of discovery that began when the spacecraft first aimed its cameras at Jupiter's cloud bands will have ended, not because the instruments broke, not because the mission failed, but because the fuel that powers them has slowly burned away according to the immutable schedule of atomic physics. And then something remarkable will happen, or rather, something remarkable will continue to happen. Voyager 1 will keep moving. The loss of power does not stop the spacecraft. It does not slow down. It does not drift to a halt like a car running out of fuel on a highway. Voyager 1's velocity is not maintained by an engine. It is a consequence of the gravitational assists it received from Jupiter and Saturn nearly 50 years ago. Those encounters gave it escape velocity, and nothing in interstellar space will take that away. No friction, no drag, no resistance. The interstellar medium is so thin that a few atoms per cubic centimetre is considered dense. Voyager 1 will coast at 17 kilometers per second for millions of years after its last watt of electricity is spent. This is perhaps the strangest aspect of the entire story. The spacecraft that we can no longer power, no longer hear, and no longer command will continue its journey as if nothing happened. Its trajectory will not change. Its speed will barely diminish. It will drift through the darkness between stars as a silent monument, carrying a golden record encoded with sounds and images of Earth, aimed at no particular destination, following a path determined by a flyby of Titan in 1980. It will not drift alone. Not exactly. Its twin Voyager 2 is also out there, also dying, also drifting, but they are not together. They have not been together since the summer of 1977, when they launched within 16 days of each other from the same launch pad at Cape Canaveral. Voyager 2 left first, on August 20th. Voyager 1 followed on September 5th, on a faster trajectory that would reach Jupiter and Saturn before its sibling. After that, their paths diverged permanently. Voyager 2 took the road, Voyager 1 did not. It visited Uranus in 1986 and Neptune in 1989, the only spacecraft ever to fly past either planet. It returned images of Uranus's tilted rings, discovered new moons, measured wind speeds on Neptune that reached 1,200 miles per hour. It did the work that the original Grand Tour had always envisioned, but the gravity assist that carried it past the ice giants also bent its trajectory downward. When Voyager 2 left Neptune, it was heading 48 degrees below the ecliptic plane, diving southward toward the constellations Sagittarius and Pavo, the opposite direction from its twin. In November of 2018, Voyager 2 crossed the heliopause and entered interstellar space. 6 years after Voyager 1, it crossed at a different distance and in a different location, roughly 119 astronomical units from the Sun, compared to Voyager 1's 122. The asymmetry surprised scientists. It implied that the heliosphere is not a symmetric bubble, but a lopsided structure, compressed on one side and stretched on the other, shaped by the interstellar wind pressing against it. Voyager 2's instruments confirmed this and added new data that reframed what Voyager 1 had measured years earlier. The two spacecraft, billions of miles apart and heading in opposite directions, were doing complementary science. Each made the other's data more valuable, and now they are both dying, both losing power at the same rate, both shedding instruments, both growing quieter. They are separated by billions of miles of interstellar vacuum, heading away from each other at a combined velocity of more than 30 kilometers per second, and neither has any awareness that the other exists. Two machines built side by side in the same clean room by the same engineers, given the same golden records, the same greetings, the same music, and then flung in opposite directions to spend eternity in different voids. They will never meet again. They will never orbit the same star. They will never pass through the same region of interstellar space. Their paths will diverge for millions of years, each one a solitary emissary heading into a separate darkness, carrying the same message from a world that can no longer reach either of them. In roughly 300 years, Voyager 1 will reach the inner edge of the Oort cloud, the vast shell of icy bodies that marks the true outer boundary of the Sun's gravitational domain. It will take approximately 30,000 years to cross the Oort cloud entirely. During that passage, it will float among trillions of frozen cometary nuclei, none of which it will come close enough to notice. It will not photograph them. It will not detect them. It will simply pass through their realm like a grain of dust drifting through a cathedral. In approximately 40,000 years, Voyager 1 will make its closest approach to a star other than the Sun. The star is called Gliese 445, also catalogued as AC plus 79 3888, a dim red dwarf in the constellation Camelopardalis. Voyager 1 will pass within roughly 1.6 to 1.7 light-years of this star. That is still an enormous distance, more than 9 trillion miles, far too great for the star's gravity to capture or redirect the spacecraft. Voyager 1 will barely notice the encounter. It will continue onward, its trajectory essentially unchanged, its golden record still spinning in silence, its antenna still pointed at a sun that by then will be nothing more than a moderately bright star in an unfamiliar sky. After the Gliese 445 flyby, Voyager 1 will continue drifting through the Milky Way galaxy. It will orbit the galactic center, along with every other star and object in our cosmic neighborhood, completing one galactic orbit roughly every 225 million years. It will never stop. It will never decay. In the vacuum of interstellar space, there is nothing to erode it, nothing to corrode its aluminum frame, nothing to scratch the golden record or dissolve the silicon in its computers. Micrometeorite impacts will slowly sandblast its surfaces over millions of years, and cosmic radiation will gradually degrade the materials. But the spacecraft is sturdy enough that its basic structure could survive for hundreds of millions of years, perhaps longer. Long after every trace of human civilization has vanished from the surface of the Earth, long after the Sun has exhausted its hydrogen and swollen into a red giant, Voyager 1 will still be out there, drifting, intact, carrying the last physical evidence that a species on the third planet once existed and once looked up. The golden record is often described as a message to extraterrestrial civilizations, and it is. But it is also something more personal than that, something the people who designed it understood even if they rarely said it aloud. The record contains 116 images encoded in analog format, greetings in 55 languages, a selection of natural sounds including thunder, birdsong, and whale calls, and 90 minutes of music ranging from Bach to Chuck Berry. It carries a message from then Secretary-General of the United Nations Kurt Waldheim, and a statement from then President Jimmy Carter that reads, in part, "As a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings." The record was designed by a committee chaired by Carl Sagan, and its creation was an act of profound optimism, the belief that something worth preserving could be placed on an object moving fast enough and far enough to outlast everything else humanity had ever built. It was Carl Sagan who, 13 years after launch, persuaded NASA to turn Voyager 1's cameras around. By February of 1990, the spacecraft was roughly 6 billion kilometers from Earth, well past Neptune, heading for the edge of the solar system. Its cameras had not been used since the Saturn encounter, and NASA planned to deactivate them permanently to save power and memory. Sagan argued that before that happened, Voyager should take one last look back at the planet that built it. NASA agreed. On February 14th, 1990, Voyager 1 rotated its scan platform and captured a series of images looking back toward the inner solar system. One of those images contained Earth. Not as a blue marble, not as a globe with recognizable continents. Earth appeared as a single pale pixel, roughly a tenth of a dot in size, suspended in a scattered ray of sunlight that happened to cross the frame. That image became the pale blue dot, and Sagan wrote about it with a clarity and emotion that has echoed through the decades since. He described the pixel as everything we have ever known. Every king, every peasant, every inventor, every explorer, every mother, every child, every civilization that rose and fell, existed on that tiny fleck of light, caught in a sunbeam by a camera that was already leaving and would never return. The photograph was not a scientific measurement. It was a mirror held up at interplanetary distance, and what it reflected back was proportion. The Earth was small, the cosmos was vast, and the machine that showed us this truth was already heading somewhere we could not follow. Imagine, for a moment, that a future mission succeeded, that decades from now, a spacecraft launched from Earth crossed the void, matched the trajectory, closed the distance, and arrived alongside Voyager 1 somewhere beyond 300 astronomical units. What would it find? Not the spacecraft you see in museum replicas or documentary animations. Those show Voyager as it looked in the clean room in 1977, bright and pristine, its white dish antenna gleaming under fluorescent lights, its gold foil insulation smooth and unscratched, its booms deployed in textbook geometry. The real Voyager 1, after half a century or more in interstellar space, would look different. Its surfaces would be weathered by decades of micrometeorite impacts, each one too small to see individually but collectively enough to sandblast the finish into a dull matte grey. The thermal blankets would be brittle, perhaps cracked in places where radiation had broken down the polymer bonds. The golden record, mounted on the spacecraft side, would still be there, protected by its aluminum cover. The cover's engraved diagram, showing a pulsar map and a stylized hydrogen atom, might still be legible. The record itself, pressed from copper and plated in gold, would likely be intact. Gold does not corrode, not in vacuum, not in the cold of interstellar space. The sounds and images encoded in its grooves would still be playable, at least in theory, by any civilization or any machine with the technology to read analog waveforms from a spinning disk. The antenna would still point toward the sun, or toward where the sun used to be relative to the spacecraft's orientation. Without power to its attitude control thrusters, Voyager would be drifting slowly in orientation, its pointing accuracy degrading over centuries. By the time a pursuer arrived, the antenna might be aimed at nothing recognizable. The spacecraft would be tumbling faintly, rotating with infinitesimal slowness in the absence of any force to stabilize it, and it would be dark. No lights, no blinking indicators, no hum of electronics. The radioisotope generators would have been cold for decades, their plutonium spent below the threshold of useful output. The computers would be silent. The magnetometer boom, the plasma wave antenna, the cosmic ray detector, all dead, all cold, all perfectly preserved in a vacuum that does not rust or rot. The pursuer would see a machine that looks almost exactly the way it did when it left Earth, except quieter, except older, except alone. A museum piece drifting at 17 kilometers per second through absolute darkness, carrying a message from a world that has changed beyond recognition since the message was written. Would the encounter matter? Scientifically, perhaps. The pursuer could photograph Voyager in detail, measuring how interstellar space had affected its materials. It could analyze the golden record's surface for signs of cosmic ray erosion or interstellar dust accumulation. It could measure the spacecraft's precise velocity and trajectory with modern instruments, refining our understanding of interstellar dynamics. But the true value of the encounter would not be measured in data points. It would be measured in what it meant, the fact that humanity had built something, lost it to the void, and then found a way to reach it again. The reunion would be proof not just of engineering capability, but of institutional memory and civilizational will. It would mean that we had learned to plan on cosmic timescales, to commit to projects that outlast individual lives, to care about something long enough to chase it across 300 astronomical units. That reunion will probably never happen, not because the technology is impossible, not because the trajectory is unsolvable, but because the commitment is unlikely. The patience is rare. The funding is easier to spend on problems with shorter timelines and more immediate rewards. That optimism now carries an undertone of melancholy. The golden record is moving away from us at 38,000 miles per hour. It is farther from Earth than any human artifact has ever been, and we cannot get it back. We cannot visit it. We cannot update it with new music or new languages or new images of a planet that has changed enormously since 1977. The record is frozen in time, a snapshot of a civilization that no longer exists in the form it was when those grooves were pressed. The people who recorded the greetings have mostly died, the languages have evolved, the political boundaries have shifted. The technology has advanced beyond recognition. The pale blue dot that Voyager 1 photographed in 1990 is warmer now, its ice caps smaller, its atmosphere altered by the same species that launched the spacecraft. The record tells the truth about who we were. It says nothing about who we have become. And this is where the question of catching Voyager 1 stops being an engineering problem and becomes something else entirely. It becomes a question about what kind of relationship humanity has with its own creations, its own past, and its own ambitions. We built Voyager 1 to explore the outer planets. It did that. We repurposed it to study the heliosphere's edge. It did that too. We sent it into interstellar space with a message for anyone who might find it. That message is still traveling. At every stage, Voyager 1 exceeded what was asked of it, and at every stage we let it go a little further, gave it a little more time, watched it drift a little deeper into the dark. We never planned to bring it back. We never planned to visit it. We never planned to catch it. The mission was always a one-way journey. The spacecraft was always meant to be lost. But there is a difference between accepting that something will be lost and confronting the reality that you could not retrieve it even if you wanted to. The first is a design choice. The second is a limitation, and the limitation is what makes the story sting. Humanity's first interstellar messenger is now so far ahead of us that even our fastest concepts for catching it require decades of flight. The machine that carries our golden record, our sounds, our music, our attempt to say we were here, is receding at a rate that our entire civilization cannot currently match. We can build probes that orbit the sun at 192 kilometers per second. We can land robots on Mars. We can photograph black holes. We can detect gravitational waves from colliding neutron stars 1 billion light years away. But we cannot touch a 722 kilogram aluminum box that we built with our own hands less than 50 years ago. That gap between capability and reach defines something true about the human moment in the cosmos. We are a species that can send, but not retrieve. We can launch, but not follow. We can build machines that outrun us permanently, that cross thresholds we cannot cross ourselves, that enter regions of space we will not visit in our lifetimes, or our children's lifetimes, or the lifetimes of anyone we will ever know. Voyager 1 did not escape from us in some dramatic act of defiance. It simply kept going, at the speed we gave it, in the direction we pointed it, and we did not build anything fast enough to follow. The loneliness of Voyager 1 is not the loneliness of abandonment. It was never abandoned. Engineers still listen for it every day. They still send commands. They still carefully manage its dwindling power with the attention of surgeons tending to a patient they know they cannot save. The loneliness is structural. It is the loneliness of an object that exists in a place no other object can reach, travelling a path no other machine follows, carrying a message that no one will read for tens of thousands of years, if anyone reads it at all. And somewhere in the opposite direction, its twin drifts southward through a different darkness, carrying the same message, bound for a different set of stars, equally unreachable, equally alone. And the question of how long it would take to catch Voyager 1 becomes, in the end, a question about whether we ever will. The technology to do it is within reach. The science case for an interstellar mission is compelling. The engineering challenges are severe but solvable. But the commitment required, a multi-decade, multi-billion-dollar mission whose results will not arrive until the middle or end of the 22nd century, demands a kind of institutional patience that human civilization has rarely demonstrated. We build for quarters, for election cycles, for budget years. Voyager 1 operates on a timescale measured in millennia. The mismatch between how we plan and how far Voyager has gone may be the deepest obstacle of all. If no intercept mission is ever launched, Voyager 1 will remain the farthest, the fastest, and the loneliest object humanity has ever created. It will drift through interstellar space for millions of years, a 722-kilogram whisper carrying the echoes of a world it can no longer hear. Its golden record will play for no one. Its antenna will point at a star that grows dimmer with every passing century. Its instruments will have been silent for ages. And somewhere on a planet 93 million miles from a medium-sized star, the species that built it will either have followed it into the dark or will still be standing on the shore, looking up, wondering whether it was wise to let the first message go without learning how to bring it home. Voyager 1 is not just far away, it is a mirror. It shows us what we can build and what we cannot sustain. It shows us what we can launch and what we cannot follow. It shows us that the hardest distance to cross is not the distance to the stars, but the distance between ambition and patience, between a species that can dream on cosmic scales and one that still plans in human ones. 15 billion miles and counting, 38,000 miles per hour, one spacecraft, no pursuit, and the dark keeps getting wider,